So we talked about how we take DNA and transcribe it to make mRNA. Now that we have our mRNA, let's translate it to make proteins. So I put it on the prokaryote side, but actually translation is the same in prokaryotes and eukaryotes. Just there's a few modifications that have to happen in eukaryotes first. We'll talk about that in the next video. So you take our mRNA over here, and the first thing that's going to happen is the small ribosomal subunit, along with a few initiator factors, are going to come along and slide along the mRNA until they find a start codon, AUG. So keep in mind this is read 5' to 3' in the RNA, and the nucleotides are read in sequences of 3, and those 3 nucleotides are what we call codons. So this over here is our start codon, and once we see that, it's going to a tRNA, which is this thing over here that has an amino acid on it. The amino acid corresponds to the codon that we find in the mRNA. So the tRNA comes and binds over here, and this happens because the anticodon is complementary to this start codon. Now, what's going to happen next is this large ribosomal subunit is going to come along. These initiation factors are not needed anymore, so they're going to dissociate. And then in this large subunit, we have 3 parts that we call the A site, or the acceptor site, the P site, or the peptide bond site, and then the E site, or the exit site. So new tRNAs are going to come in with their own amino acids on top, and they're going to come into the A site. They're going to be accepted there. Then the P site is where we're going to make peptide bonds and form our polypeptide chain of a bunch of different amino acids that we're going to get from a bunch of different tRNAs. And then after that, in the E site, this tRNA is going to leave, and then we're going to keep sliding down along, and this process will continue making a longer and longer chain. Now, when you want to finish, you're going to reach this stop codon, and the stop codon doesn't have a matching tRNA. So instead, what's going to happen is there's going to be a release factor that is going to bind over here at the A site, and it's going to make all the other tRNAs leave. This whole thing is going to dissociate, and you will be left with your polypeptide chain, and there you go, you have your protein, which now you can go and fold and modify and whatever else, so that it can be useful in the cell. Translation occurs in the cytosol, which for prokaryotes is perfect because you had a whole bunch of ribosomes, which by the way work at the same time. So you have polyribosomes doing all of this translation, but it's already in the cytosol, so you had your transcription occurring in the cytosol as well. So that makes it easier. You can do transcription and translation at the same time. So prokaryotes are a lot faster at making proteins than eukaryotes. So eukaryotic RNA has these parts called introns, which do not code for protein, and then exons that are important, that we will need. So we're going to have these little they're like ribozymes because they're enzymes, but they're not made of protein. They're made of RNA. They're going to come around, and they're called SNRPs. That's like my favorite word. They're going to come around and splice out all those introns. The introns are staying in the nucleus, and then the exons get to exit the nucleus. So here we have only our exons, and then we're going to have a G' cap, or a guanine methylated cap, and then we're going to add a poly-A tail. The G cap is important for when it's kind of like a signal for later on when we're going to be doing translation. And it's also, we're adding this poly-A tail because when you're going into this acidic environment, it's going to degrade, it's going to start like degrading these nucleotides. But if it's just a poly-A tail, it's not part of the actual exons that we care about, that's okay. So we're going to have these A's, they're going to get eaten up. That's why we have polyribosomes working on translation all at once so that we can finish it quickly before the poly-A tail runs out. Okay, so this was pre-mRNA, and now we have mature mRNA. Fun fact, this doesn't actually exist. We kind of just use this to like better explain things, but really this G-cap and the splicing of introns actually happens at the same time as transcription. The only thing that happens after is the adding of the poly-A tail. All right, so these things are kind of like say a parent who says you can't go outside unless you put on your hat and wear your sunscreen or whatever. It's kind of like you need that poly-A tail. It's an acidic world out there in the cytoplasm. So once you got that, Look, he's so mature, so grown up. They grow up so fast, man. So, you're going to be so happy. We're going to add this GCAP binding protein. Just going to come and kind of give it a hug there. And then, oh look, you've cut out all your introns properly. Okay, we'll give you an exon junction complex. And then, oh look, you added your poly A tail. Good for you. We're going to give you a poly A binding protein. And now that you have these three things, that you are able to pass through this nuclear pore complex in the nuclear membrane, and it's only going to let you through if you have all those checkpoints over here. If you do, perfect, you can go into the cytoplasm and now you can do translation.